Section 7.2, Solving Exponential Equations and Inequalities. If you haven't done so already, pause the video and try to answer these 5 problems. Let's look at the first example. 3 halves to the x equals 3 halves squared. We can assume that x equals 2. If we check it by substituting in 2 for x, we get a true statement. The next statement, we would assume that we would get 2 is less than x, or x is greater than 2. We always want to test this, so I'm going to pick a point that's greater than 2. I decided to test x equals 3, because that's greater than 2. I get 3 halves squared is less than 3 halves to the third. We know that this is true, and we could calculate that the answer is 9/4 is less than 27 over 8, which is true. On the next equation, we have 1 half squared equals 1 half to the x. So we know that again, x has to equal 2 to make this true. Now the next one is different. At first we might think that 2 must be less than x, but this actually isn't true. If you think about when you're raising 1 half to a power and then a higher power and then a higher power, your value is getting smaller and smaller. In other words, as x approaches infinity, 1 half to the x approaches 0. We'd have a half, then we'd have a fourth, then we'd have an eighth, then we'd have a 16th, if we were increasing x by integer values. This means that our inequality is actually the opposite of that. It is 2 is greater than x, or x is less than 2. We could test a point. Let's test x equals 0. If we put in 0 right here for x, we get 1 half squared, or 1/4, is less than 1. Well, that's true, which means that 0 works, so we know that our inequality is facing the correct direction. Let's look at this on a graph. Notice that all of our answers are either x equals 2, x is greater than 2, or x is less than 2. In order to visualize the situation that we just looked at, I took each side of the equation and I set it equal to y. So this here is the curve y equals 3 halves to the x, and here is y equals 3 halves. They cross when x equals 2, right here, and in our other spot over here, these also cross when x equals 2, and that was for our examples with 1 half. Notice that here we have exponential growth, and here we have exponential decay, which makes sense why over on the left-hand side on this example, our function, since it's getting bigger and bigger, when we plug in x's that are greater than where these lines cross, we're going to have a solution to that inequality that was given on the previous slide. Because over here, our y equals 1 half to the x is exponential decay, it makes sense that 1 half to the x is our greater line compared to the value 1 half, only for our smaller values, including our negatives, which would require us to flip this to 2 to some power. If the previous slide didn't make sense to you, don't worry about it. We're now going to go through examples of equations and inequalities of problems that you'll actually see. You should be following along in your notes in your packet, or you can always take notes on separate paper. Big idea. When b is greater than 0 and not equal to 1, then b to the x equals b to the y if and only if x equals y. It makes sense that this doesn't work when b equals 1, because if b equals 1, then we're just going to have 1 to some power equals 1 to some other power. Well, it doesn't matter what those powers are, those are still going to be equal. So the first step is to write our bases as the same base. I usually like to go to the lowest base. So 2 to the x I'll leave as is, but instead of the number 4, I'm going to write 4 as 2 squared. So I have 2 to the x equals 2 to the 8th, so x must equal 8, because our exponents must equal each other. You could check this, and so we would have 2 to the 8 equals 4 to the 4th. That's true. Both of those equal 256. Here's our next example. We have 2/3 to some power equals 8/27 to some power. So I have 2/3 to the 2x minus 3, and I want to rewrite this as 2/3 to some power. Now, it has to be the same power for the numerator and the denominator, and I know that to get from 2 to 8, I would cube it, and to get from 3 to 27, I would also cube it, which is good. So I could rewrite the right side of my equation as 2/3 to the third power. Now we can set our exponents equal to each other. 2x minus 3 must equal 3, and then we'll solve from there. And I get x equals 3. As always, I could check this, so I would have 2/3 to the power of 2 times 3 minus 3, which is 2/3 to the third, and that does, in fact, equal 8/27. One thing that I would suggest is that, as we previously noticed, when we're working with inequalities, our base has to be greater than 1. For equations, it doesn't matter. Notice that it just has to be any positive value, but I would suggest that instead of doing it as I just did, you actually change the 2/3 in the first problem to 3/2. That means that you would have it to the power of -1, and you still had your original exponent here. We would need to make the other side to the power of 3/2 also, which means that we have it to the power of -3. So we have -2x plus 3 equals -3 when we set our exponents equal to each other, and we still get the same answer we got before. Although both of these methods will work for equations, it makes sense to practice writing b greater than 1, not greater than 0, even for equations, so that it sets us up for success with inequalities. I'm going to do one more example. You may want to pause the video and try example C on your own, and then watch my explanation to see if you're getting it. Let's do one more example before we move on to inequalities. We have 25/16, and we have 64/125. We again want to get this to the lowest base. So I think about 25 being 5 to some power, and 16 is 4 to some power and 2 to some power. But whatever the power we raise 5 to get 25 must be the same thing that we raise something by to get to 16. So I actually need to leave this as a 4 rather than leaving it as a base of 2. So my exponent on the outside here stays the same, 2x plus 1. Now on the other side then, I need my base to be 5/4. Otherwise the problem won't work. So 64/125 is the same thing as 4 to the third over 5 to the third. So if I want to take the reciprocal of my 4/5, I need to raise this to the power of -3. In other words, 64/125 is 5/4 to the -3rd power. Keep in mind that I chose to use the base that was greater than 1. So although I could have used the base of 4/5 on both sides, it makes more sense, again, to use 5/4. So I still have my exponent, -3x plus 1. And now I can write this step out, or I can skip it. So my exponent, I actually am going to distribute because those exponents get multiplied. So I have 4x plus 2 for my exponent on the left, and I have 9x minus 3 for my exponent on the right. Now I'm at the point that I can set those expressions equal to one another. 4x plus 2 equals 9x minus 3, and I can solve. And I get x equals 1. I could, of course, check this by substituting 1 in for x here, and double checking that I get the correct answer. Before moving on, I want to quickly talk about why b has to be greater than 0. Imagine that you have a negative base, like -2 to the x. Well, think about even if you were just raising this to integers. -2 to the first is going to give you -2. -2 to the second is going to give you +4. -2 to the third is going to give you -8. You can probably see why this is a problem. We would constantly be switching between positives and negatives, and so we would not have a continuous curve. This would not give us exponential growth or exponential decay. What we could have is we could have -2 to the x. This just has a negative sign in front, so we would be taking the opposite of our exponential growth. But we would still be getting exponential growth. Remember, exponential growth can look like this, or exponential growth can look like this. It just means that we are getting bigger and bigger in terms of our absolute value versus decay, which we approach 0. Now let's move on to inequalities. Here's our big idea for solving exponential inequalities. Let b be greater than 1. We've talked a bunch about that. then b to the x is greater than b to the y if and only if x is greater than y, and b to the x is less than b to the y if and only if x is less than y. In other words, b must be greater than 1 for this to be true. So we're going to follow the same steps that we did with equations. However, we have to double check that our base is greater than 1. In our first example, we have 3 as our base on the left and 9 as our base on the right. So you guessed it, let's write 9 as 3 squared. That leaves us with 3 to the 5 minus x is greater than 3 squared to the 4th. So our exponent, 5 minus x, must be greater than our exponent 8. When I solve this, I have negative x is greater than 3, so x must be less than negative 3. I should, of course, test this. I tested this with the value x equals negative 4, because that was less than negative 3. So I got 3 to the 9th is greater than 9 to the 4th, and I know that 9 to the 4th is equivalent to 3 to the 8th. Therefore, this comes out true. I kept the greater than because I wanted to test it in my original inequality here. Here's the final example we'll do together. If you want to try it on your own, before I go through it, pause the video now. I need to make my base the same on each side of my inequality, and instead of using the base of 1/3, I know that I want to make it a base of 3. So 1/3 is the same thing as 3 to the negative 1, so I have 3 to the negative 1 to the 1 minus x is less than 3 to the 4x minus 16. So I have 3 to the negative 1 plus x is less than 3 to the 4x minus 16, and now I can set the expressions that are my exponents as an inequality and go from there. And I get x is greater than 5. I don't know about you, but I think these problems are kind of fun. Now it's your turn to try some on your own.